Okay, I think we're good to go.
Okay. Yeah. Yeah. So yeah, thanks everyone presenting LayerSkip. And a quick question: do you want to take questions during the
It's up to
presentation?
you.
Okay, I'm personally happy to take questions. Like I'm happy to be interrupted at any moment and make it like interactive. Um, so yeah, I will present the first half of focusing on motivation and training, and Akshat will present the second half on inference and conclusion. So motivation. So here we show a Llama 7B. We provide a prompt. This is a coding prompt where we ask the model, provide the model a function header and a doc string, and we ask the model to generate the body function. And we try to find, we try to early exit at each layer and see what the prediction will be. And this these colors show that indicate at which layer the correct token has been predicted. So the darker the color, the more layers were required to predict the correct token. So to show it in more detail, these are the columns show the different tokens generated, and the rows are for different layers of the model. And if you look at the very last row, we see what's the model, the final output of the model for I in range, length, numbers, and so on. And at each layer, we try to exit and show the prediction. And as you can see that, yeah, first the prediction could be gibberish because in Llama, the embedding layer has different weights from the final projection layer. So they're in different spaces, so they look gibberish. But towards the end, you see that the predict token is similar to the next token. And as you can see that for some tokens, like this token, for example, token 9, we could have exited at layer 18. Like we only, for this token, we only need 18 layers out of 32, and we could have exited there and get the same result as the final layer. For this token number 13, we require like around 24 layers. However, for example, this token 2, we required all 32 layers. So different tokens require different number of layers to predict. For this particular prompt, we found that on average, each token required on average 23 layers, 23 out of 32. So that's around a quarter of the layers we could have saved, right? So if you had a perfect like predictor to tell us, hey, at this layer you can exit because the output of this layer is the same as the output of the final model of the final layer, the best we can save is around 25%. Okay, so the question is, if we want to make LLMs faster, can we do better than that? Can we save even more layers or not? So in literature, uh, there has been like two people have focused explored early exit. How to make there are two main questions: how to make models predict tokens earlier, how do you require fewer layers for each token? The second question is uh, how to ensure that the predictions of early layers are correct, like how to know at this particular layer whether this prediction is correct and you don't need to run the remaining layers. So regarding the first question, other papers have trained additional early exit heads. Like for each layer, they train an additional head, a projection layer, but this increases memory footprint of the model. Regarding like correct prediction, they use like heuristics or additional like lightweight ML models to predict whether the prediction of a certain layer is correct or not. But again, this is also increases the memory footprint of the model. You're adding more ML modules, and you're complicating inference, adding out of like conditions and logic to determine whether to exit or not. So our paper that we're presenting today solves the first problem, like predicting tokens error uh, by adding a layer dropout schedule. So for each layer, during training or fine tuning, we skip layers stochastically to encourage models to exit earlier, and we also use early exit with a shared head. So we add the early exit loss during training to encourage the model to predict earlier, but we use the same head for all layers. And regarding inference, how to know when to exit during inference, we use self-speculative decoding, where we uh, decode, generate tokens using earlier layers and verify using remaining layers. So the rest of the talk will focus on explaining both of these in more detail. And I will focus on training, and Akshat will focus on inference. So training. So how here we talk about how we fine tune or maybe even train from scratch a model that can exit at earlier layers. We present like a training recipe where we have two components. First, we have layer dropout. So layer dropout means like during training we randomly skip each layer with a probability. However, we have uh, lower probabilities for earlier layers and higher probabilities of skipping for later layers. This way, the model is uh, more robust. Like this way, the model becomes more reliant on earlier layers because they have lower dropout rate, and become less reliant on later layers that are skipped more frequently. So yeah, this diagram is intended to show that the dotted lines are skipped more likely than the earlier layers that are solid. And the second uh, component of our recipe is we add early exit loss with a shared head. So during training, uh, after running each layer during training, we apply the final like LM head. So this is LM head here. Language model head is basically the in LLMs. This is the final layer norm and linear classifier that predicts the tokens. So during training, uh, after running each layer, we apply the embeddings to the LM head and get the predictions, and then get a loss. So we have multiple losses, uh, and we use the same head. Like unlike many other papers that require different head for each layer, we use the same head. Um, so yeah, with these two ingredients of the recipe during training, during inference, we can exit at different layers. So our model becomes like a supernet of different of models of different depths that that are capable of exiting at any layer, or let me say they are more robust at exiting at any layer. The accuracy is not as we're going to explore in detail. Okay, so the first component is of the recipe is layer dropout. Um, so basically, this is like the basic equation for transformer layer. The output, this is the transformer layer which expressed by f function f, and the output of the layer is the input plus the transformer layer operation, because we have residual connections. So we introduce a mask with a probability p, and this mask will be 0 with probability p and 1 with probability 1 minus p, and this probability increases across layers exponentially. So the first layer has 0 dropout, that never drops, but as we traverse across layers, the probability of dropping increases. We also explore doing having like a curriculum such that the probability also scales across iterations. We found that useful when printing from scratch to increase the to increase the dropout rate during training. However, during fine-tuning, we found that it didn't help. Early exit loss. So here we show the equation. Basically, this is the cross entropy loss of a language model. Usually, by default, you only apply this at the last layer. However, we get a summation of this cross entropy loss across all like all the layers, and we get a weighted average of each layer of the loss of each layer. So for earlier layers, we have a lower weight than later layers, so we don't penalize because like predicting at early layers is difficult. So we give this loss at early layers a lower weight, so that we don't penalize the prediction of the last layer. So this was the challenge we've been tackling: how to improve the accuracy of early layers without harming the accuracy of the last layer. So this was one of the techniques, which is also done in other papers, like having a weighted average of losses that increases with layers. So the weight increases with layers. Yeah. Another thing is if we apply this early exit loss to all layers during training, we will hit an out-of-memory error. So we have explored applying the early exit loss at every like 4 or every number of layers, like every 4, every 8 layers, or every 16 layers. But then found the best thing is to have some sort of rotation, some sort of curriculum where across during training different number of layers exit. So one curriculum we have tried is rotational curriculum, which means that um, let's say we have a model that has 32 layers, we can exit every 16 layers. So you only exit at layer 0 and layer 15 at iteration 0, but at iteration 1 we exit at layers 1 and 17. And then at iteration 2 we exit at layers 2 and 18. And then layer 3 we at iteration 3 we exit at layers 4 and 19, and so on. So this way, at each iteration, we only exit 2 layers, so we save compute and memory. But at the same time, throughout training, all the layers get the chance to exit. So we get the best of both worlds. Another curriculum we tried is a gradual curriculum, which means that at the beginning of training, we don't exit at any layer, but as we traverse during training, we start exiting at later layers gradually. As iterations increase during training, we add more layers to exit. So this was also another curriculum that we did as well. Okay, so the question is, when do we apply this recipe? During training or fine-tuning or what? So we tried all these, we tried different scenarios. We tried continual pre-training, which means we start with a Llama model, which is already pre-trained, and then we continue pre-training on a diverse corpus of natural language and programming language data with our recipe. We also tried to pre-train from scratch. Of course, we didn't train till the end, but this was like a proof of concept to see what's the effect of our recipe if we decide to pre-train from scratch. We also tried to fine-tune on domain-specific data. So, for example, if you heard of Code Llama, where they started with Llama and then they fine-tuned on code tokens. So we tried also to experiment our idea for this type of setting, where we fine-tuned Llama on the stack. The stack is basically a coding programming language dataset. We also tried to fine-tune on a specific task, where we fine-tuned on top v2 dataset, which is a semantic parsing dataset, where you give it where you have a task where you provide a natural language prompt, and the model generates an API for a phone. Prompts like tell me the weather today, or please call this person. These are prompts for phones. Yeah. Now we show the results. In this slide, we show the results for continual pre-training. And we have a lot of results here, but I will let's focus on one of them. So we have the results for. Okay, let me take a bird's eye view first. We this slide shows this shows the results for Llama 2.7b, and this shows the results for Llama 2.13b. And we have different tasks. The first few tasks here are perplexity, and all the remaining tasks are evaluation tasks, such as um, multiple choice questions like Pika and Sika. We also have coding like human eval, MBVP. We also have math and question answering, and also the famous MMLU, which is a college question answer dataset. And if we zoom into one of the plots, the x-axis is the layer. So and the y-axis is the accuracy. So here we try to exit at each layer and show the accuracy. So, and the blue is the baseline model. So this is like the original Llama 2 survey model that hasn't been like just pre-trained, the original model as it is. And green is our model that we have continually pre-trained with the LayerSkip rescue that I've just described. So you can see that at earlier layers, the accuracy of the baseline will drop drastically and become almost zero for this task. But our model that has been that use the recipe has a higher accuracy. Okay, if we try to exit in the middle, like at layer 16, we have higher accuracy, but still it's not good enough. We have higher accuracy with baseline, but we were hoping to get the same accuracy as the last layer, right? But yeah, but I also wanted to show that these are generation tasks where the model generates a group of tokens. These are multiple choice question tasks, Sika and Pika. We see that the drop in accuracy error layers is lower. This is a fun fact. Like I was surprised that MMLU, which is a challenging college dataset, that even for the baseline, it does quite well. It doesn't drop much at error layers. So this is like a fun fact we have found. Is there a question? I heard like a.
I had a question. Is that probably because there's some kind of leakage in the case of MMLU, if you think so? Because it's such a popular data set. Just curious if you thought if that came up.
Yeah, good question. I'm not sure why MMU in particular, but I would say in general, multiple choice question tasks are easier. There are different ways to evaluate multiple choice question tasks, but one way is you give the model a question and 4 options A, B, C, D, and you ask the model to predict just one letter, A, B, C, or D. So when you ask the model to predict one letter, that's an easier task than asking the model to generate many tokens, like in the case of coding, right? Because if you generate many tokens, then the error in one token will have an effect on the remaining tokens. So you have a compounding effect in accuracy if any of the tokens is incorrect. But when you generate one token, that's an easier task, right? Another thing is when you generate one token, you only have 1 out of 4 options to choose from. While in free-form generation tasks, you basically have all the possible tokens in the dictionary, which is like I think 32K to choose from. That's way harder task. But why MMU is doing quite well is I'm not sure. Yeah, it could be. Yeah, but the question why it does well in earlier layers. So that's really not clear. Yeah, I'm not sure why.
Yeah, but that's a thank you for that explanation.
Yeah, but yeah, but that's a combo why MMU is doing particularly better than um, other question answering tasks. Yeah. Um, and these are the results for pre-training from scratch. And yeah, and again, Like we show that the trend is not clear, but for some tasks like math, the accuracy drop is lower earlier layers. So it could be that if you pre-train the model from the start to the end using early exit, loss, and dropout, we can get like better accuracy at earlier layers. Yeah. And these are the results. So this is the result of fine-tuning on code only. So if we fine-tune on specific domain, we get significantly higher accuracy. So you see here the accuracy at layer 16 is around 10% versus I think that's 16%. Compare this to, you know, just like 3 or 4% here in the middle. So again, if you find, and also this is top v2, this special domain set, we can get really high accuracy at early. So if you only want to fine tune a specific domain, you can get decent accuracy at lower layers. Okay, this is just an ablation study where we just train from scratch and show and get the perplexity of the last layer and perplexity of the middle layers. So I think this is layer I forgot. Oh, yeah, I think this is 32 layer model. This is the perplexity layer 32 and perplexity layer 16. As you can see that, and the x-axis is the number of training tokens. So as you can see, when you train on more tokens, the perplexity on the last layer decreases, which makes sense. However, in the middle layer, we'll notice that if we don't apply any dropout, perplexity increases, and it actually increases like by orders of magnitude. You see, it increases dramatically. But if you apply the early exit or dropout, instead of increasing, it will either decrease or will increase very slightly. So this is like something interesting. We found that like transformers or LLMs, when they train, the embeddings of earlier layers divert drastically from later layers as you train. And actually the accuracy of areas becomes worse during training. This is like if you train the vanilla training of language models. So yeah, and if the more you train, the more like areas become worse. So this is like unless you apply the recipe that we mentioned. So this is like something you find interesting that could be of like considered by like for further research to understand what's happening in LLMs. Okay, so the question is like, can we get this accuracy when exiting early or not? So here this is an experiment where I provide a prompt, the capital of New York State is, and I provide to the baseline model Llama 13B, and I also provided to the to our LayerSkip model that was fine-tuned with the recipe. So if you see the baseline model, it just generated not that it generated the first token correctly. It should be Albany. Here Albany is one word, but it's 2 tokens according to the Llama tokenizer. So this goes back to the point about multiple choice question. It might be easy to predict the same token, but if to predict many tokens, it just predict the same token all the time. And yeah, this is exiting at an early 24. However, with layer dropout, it's better. It got Albany, and it generates more text. It says also capital of Albany County. It was founded and so on. But then there are some mistakes. So whatever is red here is a mistake. So we find that there are some correct tokens which is in black, and the incorrect tokens are in orange. Here the coding prompt, I just prompt with bubble sort, and he just outputs gibberish, the baseline. But the original model, it actually generated like a decent code, but there were some mistakes here in the for loop ranges. So the question is how during inference can we increase accuracy? How it seems that there are some tokens that are incorrect and some tokens are correct. So how can we fix those incorrect tokens? during inference. And this will be the part that Akshat will present. So yeah, Akshat, is there a question?
I think there's one question in chat, and I cannot go after that.
Yeah.
The question in chat is asking that MNLU, I'm assuming it's MMLU data is known to have many errors. Have you tried it on the one which has been fixed, MMLU Pro or something like that? I think that's the question.
Oh, yeah, that's a good question. Personally, I wasn't aware that there's a fixed MMLU. So if you can share the link, I'll be interested to try that. Yeah.
From my end, I have two questions. So typically, here you're evaluating for like the entire test set, probably extracting at a particular layer. Uh, as a rule, like, have you seen through the choices of schedule and other components whether there's been a consistent layer at which things stop for, on average for most test sets, and where potentially you could just prune away after that, and maybe retrain the layer skip until layer 24 or something like that, in something of that format. And another question after that would be, I'm also interested in potentially how this could be leveraged for distillation as well. Like maybe a layer skip trained LLM could, if you want to do feature transfer to a smaller LM in some sense, because you're giving more priority to the layers as well to the dropout. Is there any sort of exploration in that direction also on distillation? Does it distill better or something like that? So those are two questions.
Yeah, actually, like these are two good ideas which I haven't thought of, and I think, like by the way, we are planning to open source the models, but we're just waiting for approvals. But once the models are open source, I think people can researchers can try those. I already mentioned like pruning and at layer 24. So I haven't explored that, but I mean, looking at the at, here at the diagram, like as you mentioned, like layer 24 here has decent accuracy compared to the baseline. So you can prune here and do some few more fine tuning. Maybe someone can try layer 16, half of the model, and fine tune. So that's a great idea. And I hope like we the like the open source has been being delayed, but I think it should be done in October, and we'll maybe I can send you the link so people can play around with.
Yep.
Can you remind me of the second question? You mentioned distillation. Can you just remind me distillation between what and what, like?
Typically there's a tendency to distill between layers, right? Like you would potentially do feature level distillation between models as well. This is typically, at least in the vision side of things, the feature levels. Then I'm not entirely familiar in the LLM side, but I could also see that since we're doing some priority wise, like at the layer level, right? You're also incorporating individual representations. It might help distillation as well to a model, because maybe exiting early could also be seen as just fewer layers in the model, right? I was just curious if that lens also works, because you said it's an ensemble of multiple smaller models. So if I understood correctly, so I was just curious. Maybe you could just take a smaller model like a 1.5 billion Llama and do a distillation loss between the same attention layer at the same level or something like that. And maybe that would transfer well. Uh, it's not well formed. I was just curious if any such thought was there.
Yeah, that's another great question. I like one thing I tried was adding a distillation loss during training. So during
Mhm.
training, in addition to the cross entropy loss, I add distillation. So I added KL divergence loss and mean square. We added mean square error loss.
Mhm.
However, like the accuracy was worse, but
Mhm.
maybe like it requires more debugging or like maybe tuning like the way, because each loss we have multiple loss and I need to wait between them. Um, yeah, but I think it could be explored more. And regarding like doing pruning, we do distillation. I think it's a great idea.
Right.
Maybe that will be better than, I would say more stable than adding LX loss during training.
Mhm.
I mean, sorry, adding distillation loss during training. So maybe, yeah, I think these are all great ideas. Yeah,
Okay. Yeah. Thank you. Looking forward to the open source. Thanks for the answer.
thank you.
Mostafa, just to add on a couple more things to the point that you were saying there as well. I think one thing we have noticed is that if you were today to train a model from scratch, like a 1.5B model, versus take the LayerSkip equivalent of 1.5B, the one from scratch is likely to perform better at the current time. Now, this is probably because we fine-tuned the LayerSkip model. Mostafa was talking a lot about pre-training with the LayerSkip and the early exit loss, and that was performing a lot better. We just haven't trained a model that's gone to the same level of pre-training, like 2 trillion tokens at that point. So likely scale will solve this problem, but if we were to only fine-tune it, likely that's one delta you're going to see. The other thing is from distilling a layer-skipped model or early exit model into a normal model, it is, well, that's one thing to keep in mind, is that there could be a quality difference or something to keep in mind if you do this during fine-tuning. The other thing is that you fundamentally do change, like, or encourage a different kind of model behavior. Essentially, what we're doing is we're encouraging a refinement strategy throughout the model, where at each point we supervise for the final prediction, but we get a more refined output the further into the model that we go. And compared to the normal model, I think Mostafa had showed this earlier, this refinement strategy does kind of exist. Like you saw that slide that Mostafa had at the start where each model, each token has a different optimal layer that it exits from. So implicitly, likely due to the residual connections within a transformer, we are learning this refinement strategy as it is. We're just being a lot more explicit about it. But if you were to distill into a model that doesn't have layer skip and early exit into it, one thing to keep in mind is that we're much more aggressive about enforcing this refinement strategy than standard transformer training. So it could be better, but that's one thing to keep in mind too, is that there is like a little bit of a fundamental difference or more refinement being encouraged within our approach.
Yep, that makes sense.
Yeah. Thanks. Thank you. Okay, so maybe Akshat,
I think one more hand stuff for you.
Is there another question?
Hi.
Yes.
Can you hear me? Yeah. I do have a question. So from what I understand, I'm seeing that we are adding like the dropout layers being added to each of the attention layer, I think. Like somehow we are doing, like we are dropping later layers in the model. And is there like, I was curious whether you have thought about like doing this in a better way, like maybe instead of just using probability based dropout, we can do some like learning, because not all like at every token, maybe we don't have like we should do dropout in a better, like a more intelligent way instead of using just probability, because maybe at each token maybe the earlier layers shouldn't be dropped out, or the later layers shouldn't be dropped out. Like it depends on the token and the context of
that's a good question. Yeah. I think
Yeah.
this is the same, like similar to basically what the mixture of depth paper did by Google DeepMind, right? They for each layer, I think they added like a small like learnable router that decides for each token or for the whole batch whether to skip a layer or not. So I think that's a great idea as well to explore. Or maybe it could be during training, the router could decide to exit or not altogether, not just skip layers. Maybe, yeah. I mean, that's a great idea as well. Yeah, we haven't considered it yet.
I can share some insight from another work on mixture depth as well. Just adding on to what Mostafa was saying there too, is that one benefit that we do have in this compared to mixture depth is we do retain a static graph in what we do. There are essentially 2 fixed exit points, which makes the KV cache management a lot simpler, batched inference a lot simpler and such. For mixture depth, you can change the exit point, or anything with dynamic inference, you can change the exit point at each layer per token, which means if you're trying to batch together a series of requests, it gets a lot trickier. Because if essentially one model is taking up layers like 1 through 16, another one takes up layer, or another sample only needs up to layer 8, we batch this together. We have to be a little bit more clever on how we restructure the KV cache and how we do like the batch inference and repat everything. So there are more engineering challenges And I know Mostafa has a ton of thoughts on this one as well from our discussions too. But there is a simplicity aspect, which is both like the cost because we don't have dynamic exit at this point, but also the benefit from an easier inference stack to work with.
Okay, yeah. So I think I can hand over to Akshat. Do you want to share your screen or?
Yeah, it might just be a little bit easier on you if I share the screen.
Yeah.
All right.
Okay.
Let me do that. Oh. Actually, Mostafa, I might not have given Google Chrome permission to share my screen. Do you mind if you do it? Okay. And I can just do. Oh wait, actually, I think we're good. We're good.
You have okay.
Nope, we're not good. Can you share?
Okay. Okay. You can see my screen now, right?
Yep, I can see it. Awesome. We can go to the next slide.
Oh.
So Mostafa talked a lot and like kind of left us on this cliffhanger on how do we actually fix inference for generation. So before we directly answer that question, I just want to bring everyone up to the same page and we'll just go a quick background into LLM generation in inference. So LLM generation has two key steps that we exploit and a lot of other work exploit here as well. So just summarizing them to start off with, first the prefill step and the second is the autoregressive generation step. So the prefill step is essentially what you do when you have a prompt. Your goal is if you're given a set of tokens to be able to encode them to start autoregressive generation. The key insight is that this can be computed fully in parallel, like all tokens can be done independent of each other because of the nature of the transformer architecture and being able to leverage a causal mask that avoids feature leakage of tokens. So while this actually computes the same number of nodes as autoregressive generation, the fact that this is parallel in nature makes this significantly faster, orders of magnitude traditionally, than autoregressive generation. And like an example shown in the figure right here. Like if you give a prompt to sequence T1 to T4, the dark green tokens, everything is computed fully in parallel, and you produce token T5 as well as the states for tokens T1 through T4. Next slide. Autoregressive generation ends up being a bit more challenging, and this actually is sorry.
Is something wrong?
No, we're good. I thought someone was saying something.
Okay.
So for autoregressive generation, this is a key part of LLM generation. This can end up being the largest bottleneck in most solutions. And what this is that after you've encoded in a prompt, you want to generate a token by token output. And the issue here is if you look at this figure here, that if you have token T4 and you want to generate T5, you actually have to make a decision off of the distribution of what token T4 is, what predicts T5 is. And selecting that token is a sequential decision problem. So even though it's the same computation that's done, the sequential nature of the process, it makes this linear in nature compared to essentially constant with parallel, with some caveats on how it's implemented. There are things we can do to speed this up. Like for instance, we can cache the KV cache. So that's what's shown in this figure here, that if we have token T4, we've actually computed T1 to T3. That's the light green states. And we only need to feed in token T4 through the model. And it can be clever on how we reuse states from prior. But even with that, this ends up being a pretty key bottleneck in how we do inference in our model. Next slide. So with these two insights, there's been a lot of work on speculative decoding. So to give a brief overview of that, this is a very popular inference algorithm. A lot of folks use it for inference. It's a guaranteed lossless way to speed something up. And it relies on two key insights. One, we know prefilling is fast because it's fully in parallel. And two, token by token generation is slow. So what we do is we take a small model, termed a draft model, shown on the left side here, like in this case, a 2-layer model. And we use that to do token by token generation. And because the model is slower, this will be a lot faster than doing it out of our main model. And what we do instead is in our main model, which is shown on the right here with all 4 layers, is we take in all these draft sequences generated by the smaller model and we verify them with the larger model. And what that does is we can verify that a sequence is correct fully in parallel because we feed in the full sequence, T1 to T4, If it's entirely correct, we just continue generating from the small model. If there's any mismatch between the predictions of the large model and the small model, we'll just continue generations from the last match from the large model here, with the next token predicted from the large model. So we can guide the small model on what's to be done here. And the key thing is, as long as this agreement rate between the small model and the large model is relatively high, which ends up being, if you can train the small model pretty appropriately, this can give you a pretty decent speed up on decoding, which is why it's favored by several folks for deployments. The key thing is that the draft model has to be small and agree with the larger one. And the other thing is it ends up being guaranteed lossless, because anytime there's a disagreement from the main model and the small model, you will select what the main model had predicted at that point. So even in the case where you had a completely garbage small model, you will still be guaranteed to have the exact right output at the cost of latency. Next slide. Okay, so we talked about speculative decoding. We talked about how it's very impactful and being used everywhere. So there is a problem with this, though, and it's this entire concept of being able to train another model. One thing is that if you're familiar with language model training, it's an expensive and cumbersome process, and it's hard to get right at times. And also, in the case of inference optimization, you have to really care about what your latency requirements are. Every time you want to speed something else, you have to design not only a model that has a high agreement with the main model you're trying to optimize, but you also have to design a model that's inference aware and something that you are comfortable with the speed running for the majority of queries. So training a large language model, another one, even if it's smaller, is a cumbersome and expensive process. The second thing is that if you start moving to more resource-constrained devices, where we want to start supporting more users on our servers, we want to support cell phones with local deployments, where the cost of a single LLM is difficult enough, storing a second model is often prohibitive. So this enables disabling areas where we need the speed up the most, like edge devices. So now, connecting back to what Mostafa was talking about earlier, the key insight here, which I think someone had brought up earlier as well, is that layer-skipped LLMs are supernets. And what I mean by supernet is it's this property that a single LayerSkip LLM is not just a single model. It's actually a family of models at n different models with n different sizes and n different quality benchmarks. And here, critically, n is the number of layers. I can easily go and I can trade off what I want the latency of my model to be by choosing the number of layers I exit from, as well as what the quality will be. And the nice thing about this is that compared to like any sparsification, pruning, sparse inference work, anything like this, we are just creating subsets of transformer models. They are the exact same transformer model, just with fewer layers, or different number of layers in each setting. Which means for inference stacks, largely the unit that you operate on top of is a transformer layer. So this ends up plugging and playing very nicely with existing inference solutions. So now the question becomes, this insight that a single layer-skipped LLM is a supernet, can we exploit this such that the same model can serve as the main model that we want to produce the highest quality output from, as well as a draft model that we use for speculative decoding? And this process, we and others in the field term as self-speculation. Next slide. Okay, so now going a little bit more into what self-speculation looks like, the main idea is there. The main idea is you take the first E layers of the model and you use that for drafting and use the remainder of the full model to verify. So an example shown on the right here, that at the drafting stage, we still have the full model being allocated, in this case, all 4 layers. But when inference comes for tokens T1 to T3, we go through the first 2 layers, because E equals 2 in this case, and we skip directly to the output for generation. So this ends up being our drafting mechanism, which is as fast as a 2-layer model for inference by design, without allocating it. On the right-hand side, when it comes to the verification step, we can actually take the full model and run full parallel verification over it. And because of all the properties we talked about, we do get a guaranteed output that matches the full model here. And this is easier because now we can actually just directly control the quality and latency we want from our draft model by just changing the number of layers here, depending on our task domain, use case, and inference requirements that we want to be optimizing for. Next slide. On top of this, specifically because we do early exit inference in this way, that we have not only a strict subset of our model, but a strict subset of the control flow our model takes at each step, we can exploit this a bit further and even optimize for a single KV cache, which speeds this up. And the idea here is that when we're computing the full model's verification step, we actually don't need to recompute layers 1 and 2 or up to layer E, because we already computed the exact same token, like T1, T2, T3, conditioned on T1 and T2 respectively, through our drafting phase, which ends up saving a lot of compute. And this is actually a pretty big deal because let's say you're layer skipping half your model. It means at the verification step, you can actually save about half the compute because you don't actually need to run the majority of the layers or half the layers during that step, which also speeds things up. Next slide. This just shows that we are realizing gains from doing this KV cache saving. So at this point, we don't only just have the same model, we also have the same KV cache, making this very memory optimized solution for enabling self-speculation. Next slide. All right, the main thing I want to walk through here is that this insight and property we exploit from LayerSkip LLMs is actually just very much the exact spec decoding algorithm with very slight differences. So next slide. We still use the earlier layers to draft tokens. This is your average pseudocode on the right-hand side for self-speculation. You can just plug in using the earlier layers as a drafting mechanism. Next slide. Use the later layers to verify the model, which is the verification step. And next slide, you update the KV cache. And the point here is anywhere you can now implement speculative decoding, you can now implement self-speculation with the LayerSkip model. And this will give you the direct memory savings you need to deploy in resource-constrained environments. Next slide. All right, now into the algorithm itself. There's two key parameters that you have to consider when enabling self-speculation. First is early exit. What is the layer that you want to exit on top of? Selecting something too small, it's fast, but it's garbage, and you're going to end up with too many misses in the verification phase and just keep wasting. You're essentially running the large model too many times. You'll take on the cost of autoregressive generation. So that's not something you want. And too large, it is just the full model at that point. And you're not going to be able to realize speedups. So you need to be careful about the early exit layer that you select. And the other aspect you need to be careful about is the number of speculations, the draft size that you do before verification. Something too small and you're just checking too frequently. And it's the same as running inference in the larger model, so you're not going to really speed anything up. Something too large and you might miss the token, end up wasting a lot of compute and have to start over again. Also hurt in latency. So these two things are the things you have to trade off when you're building out what is self-speculation for your stack. Next slide. So what we present here are a couple of heat maps on what exactly this performance looks like. So on this x-axis, you have the exit layer that we can pick out of a 7B model. We're looking at about 0 to 16 or 0 to 20 in these cases. And on the y-axis, the number of speculations that we're doing. And the darker the color is on this heat map contour plot is the tokens per second. So what you see is that on the left-hand side, there's human eval, a coding-like task. And on the right-hand side, not coding-like, this is a coding task. On the right-hand side, you have CNN Daily Mail, which is a summarization task. And you'll see that the points that we optimize for are quite different and end up being data, domain, and task dependent. Where you can see the cluster points is a lot lower on the number of speculations for coding, likely because there's a lot more pivotal points to be made on like what exactly the bounds for your function, what are the parameters that you want to be using, and you essentially want to be speculating what the boilerplate code is. Whereas for summarization, it's a lot easier to speculate for longer windows. So you end up with this optimal point for hitting speedups being a lot higher in the speculation window. Next slide. And we actually take a further look at this and we look at the acceptance rate across the small model and the large model here. Looking again at human eval and CNN Daily Mail. They might be actually swapped on this slide, so keep that in mind. But the point holds the same, that the darker the color here is, the higher the acceptance rate at this point. But if you remember, the cluster of points on both images is roughly where the optimal tokens per second is. And for acceptance rate, it's they're pretty primitive solutions here, or degenerate solutions here, which is one, you can get a very high acceptance rate by increasing your exit layer. But again, that comes at a cost of latency, so that's not quite what we want. And if we go all the way to the left, we're just going to have a garbage model, and acceptance rate is going to be too low. And what we find is that the optimal point always lies right on this cliff of performance, where it's right about good enough where we can get a decent enough acceptance rate with a small enough exit layer to realize the wins. And you see that across both settings, that you really just want that point on the cliff where the models are just good enough to get an acceptance rate that's feasible for speculative decoding, and that's when you're optimal at latency. Awesome. Next slide. Now, quickly going over the full results from this speculative decoding, or self-speculative decoding. We start off by showing off just fine-tuned models. So you can take Llama 2.7b, fine-tune it with the recipe that Mostafa talked about, leverage self-speculative decoding algorithms. You can actually have pretty decent speedups across model sizes. So a lot of prior work in self-speculative decoding requires a much larger model to be able to realize the wins here. Because you are skipping a decent chunk of the model, you do need to have like essentially a critical mass that we're using. What we found with LayerSkip and early exit is that, is that we can speed things up quite a bit, even in the smaller models like that 7B scale. And we actually even saw this go down to 1B in some of our experiments as well, that we do keep seeing a consistent one across model sizes. And we're getting like 1.8x improvement, again, keeping quality consistent when using LayerSkip models with self-speculative inference. For generative tasks, keep in mind these are all generative tasks that we're looking at compared to what we were looking at earlier. Next slide. Now, we also present early results on pre-training. Keep in mind everything was done during fine-tuning in the prior stage. When you take a 7B model and a 1.5B model and you pre-train it for even like 30 billion tokens, we can see that we're actually speeding up performance quite a bit. We went from 1.8x to 2.2x rather quickly. And we believe that as we continue to scale this up, we'll continue to realize more and more wins. And we're continuing to work on this direction. Or more specifically, at this point, Mostafa is continuing to work on this direction. But it's quite exciting that we're seeing that if the earlier you inject LayerSkip models, the longer you train for them, the faster you're realizing not only the quality wins, but also the inference speedups that you can leverage for your tasks. So next slide. Now, briefly going over conclusion and future work. So again, without any additional modules, without any additional memory footprint, we can enable the improved accuracy of the earlier layers, which ladders up into speculative decoding within a single model in a single KB cache, really making this optimal for any memory-constrained deployment scenario. And there's a potential for even more speed up if we continue to push on pre-training, which makes us very, very bullish that LayerSkip models are a strong way forward for efficient inference and efficient training. Next slide. And just hinting more at what our future work is and what we encourage others to take a look at as well, is one, pre-training continues to be the way forward. Scale is important. You can realize once through fine-tuning, and we can continue to say that as well, which we'll talk about in a second. But for pushing out maximum performance, we are strong believers that it is scale, that we need to go over for larger models, more tokens, and continue to see how our experiments do at the larger scales. And the second is for folks that are working on fine-tuning. One thing that we talked about earlier is that we did a lot of work on how to minimize the loss that we see in quality. And all the stuff that we talked about around how we incorporate the schedules of including the early exit losses, how we train these models are all about how do we minimize quality loss from training from LayerSkip and early exit models, which we have done. Another line of work is to consider what happens when you use LoRa for all the early exit training instead, which has more strong guarantees on keeping the original model performance, and then we use fewer parameters to learn this early exit module. Which we also believe is quite promising for taking an existing model and adapting it to have this early exit LayerSkip property on top of that. I think that marks the end of the part that Mostafa and I had here. So we can open up for questions for a few minutes.
I have one more question. Is like, did you see that? I think there was one question I had initially which got answered is like, okay, if you have larger models, probably you're getting better benefits. That's nice to know. One more loss for us with pure GPUs. But I was also curious whether at different stages you saw, like, did you evaluate this self-speculation capability getting worse or better with different stages of the LLM cycle, in some sense that if you just have a pre-trained LLM and you do self-speculation there, then you have like fine-tuning, instruct tuning, etc. Do you see like what the trend is there in broad?
Yeah. It's a great point. So we actually, there's two ways to answer your question. So I'll do both. Let me know if you want to dive into data for each one. One is that we apply this as a fine-tuning step on top of any base model. It's whether that base model is a pre-train only model or in a pre-aligned model. And the truth is that it just matters what your fine-tuning data is. So for the task where we did on top of the fine-tune model, we tried to teach it some specific domain on top of it, whether it was coding or conversational assistance or something like that. But as long as we were training within the domain that we're evaluating within, it didn't matter what the base model was. It would essentially just follow the same recipe as traditional fine-tuning. Now, so it would work in both scenarios pretty much equally, like we noticed uniform speedups at that point. Now the question is it whether you inject the LayerSkip at the fine-tuning of the pre-training stage. And at that point, the earlier you inject LayerSkip training, the better the performance is going to be for self-speculation. So if you pre-train with LayerSkip, or even just do it early in the process, or train longer with LayerSkip, that'll always be faster performing and better than later into the model. But it still works with later into the development cycle. But it still works later into the development cycle quite well. Does that kind of answer your question?
Yep. Yeah, I was just also curious because I think Virat's paper also recently talked about how, adding code to the pre-training basically makes it better for like other tasks as well, right? So I was thinking, like, is there a specific flavor or sort of like a particular domain of data that you'd add to the mix that essentially makes self speculation better? I was also curious about like what affects this ability to self-speculate beyond sort of also the fact that you're adding LayerSkip. Like, is there certain kinds of data that you were just better at? That was also something I was curious about.
Yeah, I would like to mention that, like, I mean, this was something we noticed on baseline model without any LayerSkip, that coding tokens usually, if you have a coding prompt, usually the model predicts tokens earlier compared to natural language prompts. I'm not sure why, but it could be that with natural language, like, you need more layers to refine, the output to choose which word to use, this or that, or which, or. But with coding, it's because it's like it's more like deterministic, and you are confined by syntax rules. So usually, maybe you need fewer layers to decide which token to predict. So this is something I have noticed, that in general, coding prompts require fewer layers than natural language.
Yeah. And probably one last question because we are also in Super AI. So, did you see any interesting trends or like any evals which are like multilingual in some sense? Like maybe other languages other than English, and like see that there was any. Was it the similar performance, or was it like somehow, yeah, if at all, that was explored?
Yeah, good question. Like, we haven't, like, evaluated those multilingual benchmarks. So yeah, that's a good question. Yeah, there was an interesting paper in ACL. I think if you can search for it, do LLMs work in English? And they found that, like, they're giving it a prompt, and like, let's say one of the examples they show that if they give it a prompt to translate a word from Chinese to French, and when they investigated the outputs of each layer, they found that in the middle it translated to English.
Oh, that's cool.
It translated from Chinese and erased to English, and then back to French towards the end. So yeah, this is just something interesting. I've not sure how it's related to this, but yeah. But I would imagine it might be maybe more challenging to exit area with multiple languages, if this is, according to that paper. But one thing I also wanted to mention is that we noticed that it's like, we didn't do enough ablation studies, but it seems that if you train a large model from scratch using LayerSkip, you might get better speed up. But if you do continual pre-training, small models are better. Larger models, they might have a bigger drop in accuracy for the last layer, and we need to way more tokens, like train on more iterations to increase the accuracy of earlier layers. It could be related to this plot here, that if like, I think when the model is bigger, this difference in if a model is pre-trained from scratch and on so many tokens and iterations, the earlier layers have way worse accuracy. So if you want to do continual pre-training using LayerSkip, you need a lot of training iterations to reverse this effect and damp and drop this gap between earlier layers and last layer. So yeah, this is just something to mention. Yeah.
I have one last question, if it's okay. I don't know if Virat will allow me to, but and if possible, one last question is, uh, did so was inference? At what precision did inference take place? Like, did you see any impacts of that in terms of quantization on the ability of the of self speculation to work better? Because typically inference is being very aggressive, right? Like for the larger model, like 7B and those kind of things. Was there any impact of that, I assume?
Good question. Actually, there's a paper we working on and hopefully publish soon. But
Okay.
we tried to combine LayerSkip with 4-bit quantization, and so I mean, okay, there's a mix. As for small model, we found limited combined speed up. Like we combined mode, there was no speed up. And sometimes it was slower. But with the bigger model, like the 30, we did code Llama 34B, there's actually combined speed up. So yeah, it depends on the model, depends on the size of the prompt and whatnot. But it seems that for bigger model, combining LayerSkip quantization can lead to combined speed up.
Right.
So yeah, that's and this was 4-bit quantization, weight only.
Yep. Because somehow I can see, like, if you do dynamic quantization, skipping layers might be nice for you because you don't need to go so deep in the model, in the forward pass. So
Oh, you need dynamic quantization during training?
yeah, like not more like at inference time, right? Like dynamic quantization. I think some of them do that, right? Like I think in Torchio we were attending a talk 2 weeks ago. So
Was that 8-bit or 4-bit?
I think that was 8-bit. I think it's 8.
Dynamic quantization ends up working a lot better because I think you can essentially do 8-bit post-training quantization with very little accuracy loss compared to 4-bit that Mostafa was talking about. What we've essentially seen is that when you go sub around 6-bit, you need to start doing something that influences the training recipe as well, which is when quantitative training comes in.
Yeah. No, but I also thought like maybe just that overhead of having to do fewer quantization steps is nice, I think. Like because you have fewer layers you're going through, right? So I thought that would be a nice thing to test it out. Yep, sounds good. Thanks for your time and all those patient answers to my questions. It was really great having you here.
Yeah, and thanks for all the discussions.